Okay, this video is about regression towards the mean, and we're going to use these formulas that we just worked with to help develop this concept. First of all, just a reminder that the least squares regression line always goes through the point x bar, y bar. I mark that point on this graph. So this graph is the graph of the data that we just were talking about, the unemployment rate and murder rate example. There's the equation of the line. Notice I have this point marked where we have the mean of y and the mean of x. So this is the point x bar, y bar. And the regression line always goes through that point. In this case, the mean of the x value is 6.935 and the mean of the y value is 20.57. Okay, so I've got those written over here. And then I also marked where one standard deviation above the mean was in both x and y. So if I add one standard deviation to x bar, I get this value 8.14212, and if I add one standard deviation to the y bar, I get 30.4514. So this point right here where those two values cross is the point 8.14212, comma 30.4514. That's this point right here. But notice that point is not a point on the line. The point that's actually on the line is right here. The x value is the same, 8.141212, but what is the y value? So that's what we're going to be talking about. There's a concept called regression towards the mean, and basically what regression towards the mean says is that unless the correlation is perfectly 1 or -1, a one standard deviation increase in x only predicts less than a one standard deviation increase in y, or decrease, depending if it was slanted up or down. And the way we can look at this, exactly how much this value is can be determined using the slope formula. Since b1 equals r times the standard deviation of y over the standard deviation of x, we could also write it as r times the standard deviation of y over the standard deviation of x, which means that a one standard deviation change in x predicts an r standard deviation change in y. So this is actually slope. The change in r standard deviations in y is predicted for every one standard deviation change in x. So what that is telling me is that if this is one standard deviation in x, then this is r times one standard deviation in y. So how does this work out in calculations? So if I know that well, let me go ahead and write this down. So in this example, when x increases by one standard deviation, so this is standard deviation of x right here, the regression line predicts y to increase by r times one standard deviation in y, or 0.864841 times the y standard deviation is right here, 9.88141. And if I multiply those together, I get 8.54585. So instead of going up one full standard deviation in y, which is 9.88, it only goes up 8.54, which is a little less than one full standard deviation in y. So this value should be the mean of y plus r times one standard deviation. So if x equals the mean of x plus one standard deviation plus, I'll just say s of x, one standard deviation of x, which is 8.14212, then y hat is equal to y bar plus r times s sub y, which would be 20.57 plus 8.54 1.585, which turns out to be, and I should be looking at this number here, this turns out to be 29.1159. So that's odd that it would be 5.9. Looks like it should be 5.5 at the end. Interesting. I'm going to double check this number. Yeah, that's the number I got, and I just realized that's a rounded number at the end. It's probably 1.585 or, you know, something 5 at the end, and it rounds up. So no problem, we'll just leave it like that. Now, let's double check. That's what we say the predicted y should be based on what's called regression towards the mean. In other words, the y value is closer to the mean of y than the x value is to the mean of x in terms of standard deviation. That's what regression towards the mean means. So now let's use our actual regression equation. Negative 28, so if we kind of scroll up a little bit here, here's the equation, negative 28.5267 plus 7.07955. Now, if we put in that x value that I just used, so if x equals this, 8.14212, then what I get for y turns out to be, if you do this on the calculator, 29.1158. So once again, it's just a rounding issue here, but that is the predicted value turns out to be y bar plus r times the number of standard deviations in y that match the number of standard deviations in x. Now it turns out if I were to add 2 standard deviations in x to x bar and want to know what the predicted y was, this would be just r times 2 standard deviations in y. But you always multiply it by r because this is telling me that there isn't perfect correlation. If there were perfect correlation and r was 1, then the line would actually go through this point. 1 standard deviation of x, 1 standard deviation of y, because each standard deviation of x would exactly predict a 1 standard deviation increase in y. But because the correlation is not perfect, then we have regression towards the mean. If you look at the printed notes, I kind of summarized this, and I think maybe I will just go ahead and write this down for you. I'll pause the video and write this down, kind of a summary statement here. 1 standard deviation increase in x predicts an r standard deviation change in y. And so if this were 2 standard deviation, and that's true for each standard deviation. So if this were 2 standard deviation increase in x, that would produce a 2 times r standard deviation change in y. Couple more points here. Can we say that a higher rate of unemployment causes the murder rate to increase? No. We can only say that there is an association between the 2 variables. We can only determine cause and effect if there were an experiment, and it would be impossible to do an experiment in this case. You know, randomly assign half the people to be unemployed and half to be not unemployed and then see who got murdered more. No, that would not work. So we can only say there's an association. Here's the issue. We might have one of 3 things happening. We might have, that's supposed to be 3, number 3. See if I can write a little better. Number 1, we might have x causes y. We might have y causes x. And this would be for any particular association that we're talking about. Or we might have another variable causes the observed change in both x and y. Now we talked about this actually in another chapter, or maybe depending on what year this is, maybe we haven't talked about it yet, but let's say we have an example where there's a positive association between air conditioner sales and the number of drownings. Okay, so people drowning, all right? And there's some sort of positive association here. Well, it would be ridiculous to say that if people buy more air conditioners, then that's going to cause more people to drown, or drownings cause people to buy more air conditioners. Neither of those makes sense. What does make sense, though, is to say when the temperature increases, people buy more air conditioners. And when the temperature increases, there are more drownings because more people are swimming. So there's an example of an underlying variable causing the observed change in both X and Y. I use that example because I actually can't think of an example of an underlying variable that would cause this particular association between unemployment and murder rate. The reason why that's important to talk about cause and effect is because we cannot determine cause and effect, then a person who's working with this data can't say, oh, if we could just figure out a way to lower the unemployment rate, we would solve the murder problem. Well, we don't necessarily know that that's true because there might not be a direct cause and effect relationship. It might be that that's true. It might be that the murder rate would go down if more people were employed, but then again, it might not. So you have to be careful when you're talking about cause and effect when you're dealing with this kind of data.